Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on zeros of an analytic function. Firstly, we defined the zero of an analytic function. Let function of z is analytic in a domain D which vanishes at z equal to z naught and function of z is analytic in the neighborhood modulus of z minus z naught less than r, then z equal to z naught is called the zero of the analytic function of z. That is, function of z equal to 0 at z equal to z naught and function of z is analytic in the neighborhood of z equal to z naught. Then z equal to z naught is the zero of the analytic function. Example 1. Let function of z equal to z minus 5 by z square plus 2. Since at z equal to 5, if we put z equal to 5, this becomes 5 minus 5 0, 0 by this is 0. That means at z equal to 5, function of z equal to 0, therefore z equal to 5 is a 0 of function of z. Example 2. Let function of z equal to z minus 1, z minus 3, z square plus 16. Since for z equal to 1, if we put z equal to 1, this becomes 0. That means numerator will be 0. That means function of z equal to 0. Function of z equal to 0. Again, for z equal to 3, function of z equal to 0. Therefore, z equal to 1 and z equal to 3 are zeros of function of z. Example 3. Function of z equal to sine 1 by z. Function of z equal to 0 implies that sine 1 by z equal to 0 implies that 1 by z equal to n pi n belongs to z set of integers implies that z equal to 1 by n pi. N belongs to z. Therefore, function of z equal to 0 at z equal to 1 by n pi. Therefore, z equal to 1 by n pi is the 0 of function of z. Now we describe about the 0 of order m of an analytic function. Since from the definition of zero of an analytic function fz, we know that z equal to z naught is called the 0 of the analytic function fz if a function of z equal to 0 at z equal to z naught and function of z is analytic in the neighborhood z minus z naught less than r of z naught. Therefore, function of z may be expanded in Taylor series as follow. Function of z equal to sigma n equal to 0 to infinity an z minus z naught whole to the power n, where an equal to nth order derivative of the function at the point z equal to z naught by factorial n. This is number 1, this is number 2. Therefore, function of z equal to a naught plus a1 z minus z naught plus a2 z minus z naught whole square plus dot 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 plus a m minus 1 z minus z naught whole to the power m minus 1 plus a m z minus z naught whole to the power m plus a m plus 1 z minus z naught whole to the power m plus 1 plus dot 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 dot. Let this is number 3. If a naught equal to a1 equal to a2 equal to dot 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 equal to a m minus 1 equal to 0 and a m not equal to 0, that is here a n equal to nth order derivative of function of z at the point z naught by factorial n. If a n equal to 0, that means nth order derivative of the function at the point z equal to z naught is 0. That is function of z naught 0, derivative of the function at the point z equal to z naught equal to 0, second order derivative of the function at z equal to z naught equal to 0, dot 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 dot, a minus 1th order derivative of function at the point z equal to z naught equal to 0, mth order derivative of the function at the point z equal to z naught not equal to 0, then function of z equal to this 0, that means am z minus z naught to the power m plus am plus 1 z minus z naught to the power m plus 1 plus dot 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 dot, and we may take this z minus z naught whole to the power m common am plus am plus 1 z minus z naught whole to the power 1 plus dot 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 dot. This is equal to z minus z naught whole to the power m. This is phi z. Let this is number 4. In 4, if we put z equal to z naught, then function of z equal to 0. Here if we put z equal to z naught minus z naught whole to the power m, 0 to the power m, this is 0, that is right side 0. And since we have z minus z naught to the power m in right side as factor, so z equal to z naught is a 0 of the function fz, but this 0 is called 0 of order m. Therefore, z equal to z naught is said to be 0 of order m of function of z if a function of z naught equal to derivative of function at the point z equal to z naught equal to second order derivative of the function at the point z equal to z naught equal to dot 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 equal to a minus 1th order derivative of the function at the point z equal to z naught equal to 0 and mth order derivative of the function at the point z equal to z naught not equal to 0. Now we prove a theorem. Theorem is let function of z is analytic in a domain D, then unless function of z is identically 0, there exists a neighborhood of each point in D throughout which the function has no 0 except possibly at the point itself. In other words, the 0 of an analytic function are isolated. Now we prove this. Given that function of z is analytic in a domain D. Let z equal to z naught is the zero of the function of z, then function of z equal to 0 at z equal to z naught, and function of z is analytic in the neighborhood modulus of z minus z naught less than r of z naught. This is the neighborhood of z naught. Therefore, function of z may be expanded in Taylor's series. Therefore, function of z equal to sigma n equal to 0 to infinity a n z minus z naught whole to the power n, where a n equal to nth order derivative of the function at the point z equal to z naught by factorial n. Let this is number 1 and this is number 2. Implies that function of z equal to a naught plus a1 z minus z naught plus a2 z minus z naught square plus a3 z minus z naught cube plus dot 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 a minus 1 z minus z naught to the power a minus 1 plus am z minus z naught whole to the power m plus am plus 1 z minus z naught whole to the power m plus 1 plus dot 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 dot. Let z equal to z naught be the zero of order m, then a naught equal to a1 equal to a2 equal to dot 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 equal to a minus 1 equal to 0 and a m not equal to 0. This is number 3 and this is number 4. Using 4 in 3, we get function of z equal to am z minus z naught whole to the power m plus am plus 1 z minus z naught whole to the power m plus 1 plus dot 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 dot. Here we take z minus z naught whole to the power m, am plus am plus 1 z minus z naught whole to the power 1 plus dot 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 is equal to z minus z naught whole to the power m. This is function of z, where function of z equal to am plus am plus 1 z minus z naught plus am plus 2 z minus z naught whole square plus dot 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 dot. Let this is number 5 and this is number 6. Z equal to Z naught is called 0 of order m if a function of z equal to 0 in 5, 6 may be written as function of z equal to sigma n equal to 0 to infinity a m plus n z minus z naught whole to the power n. This is number 7. Therefore, 5 may be written as function of z equal to z minus z naught whole to the power m sigma n equal to 0 to infinity a m plus n z minus z naught whole to the power n. This is number 8. Putting z equal to z naught in 6, we get function of z naught equal to am. Here z equal to z naught, this is 0, this is 0, only remains am. And since am not equal to 0, we have already assumed it. This is number 9. Since function of z is analytic in D, therefore from 6 phi z is analytic in D implies that phi z is continuous in D, since every analytic function is continuous. Therefore, for epsilon greater than 0, there exists delta greater than 0. We have phi z minus phi z naught modulus less than epsilon for modulus of z minus z naught less than delta. This is number 10 and this is number 11. Now let epsilon equal to modulus of am by 2. For this, let delta equal to delta 1. This is number 12. This is number 13. Using 12 and 13 in 10 and 11, we get here modulus of function of z minus function of z naught less than modulus of am by 2 and modulus of z minus z naught less than delta 1. This is number 14. This is number 15. If possible, let function of z equal to 0 in the neighborhood modulus of z minus z naught less than delta 1. Let this is number 16. This is number 17. Using these in 14 we get modulus of function of z equal to 0 minus function of z naught less than modulus of am by 2 implies that modulus of function of z naught less than modulus of am by 2 implies that since we know that function of z naught equal to am, here 9 am modulus less than modulus of am by 2 using 9. Here left side is modulus of am and right side is modulus of am by 2, which is not possible, which is not practically possible. Therefore, our assumption in 16 is wrong. Therefore, function of z not equal to 0 at other points in the neighborhood z minus z naught less than delta 1. Also, if a z not equal to z naught implies that z minus z naught not equal to 0 implies that z minus z naught whole to the power m not equal to 0. Let this is number 18 and this is number 19. From 18 and 19 we get z minus z naught to the power m function of z not equal to 0 at other points in the neighborhood z minus z naught less than delta 1. Other points means except z equal to z naught, and at other points this is not equal to 0 and this value is function of z not equal to 0 at other points of the neighborhood. Therefore, there is no other points in the neighborhood of z equal to z naught for which function of z equal to 0. That is, if z equal to z naught here, at this point function of z equal to 0, But in the neighborhood, if we take any other point, let z equal to z1, function of z1 not equal to 0, here z2, function of z2 not equal to 0, means except this point, the value of the function is not 0 in other points of this neighborhood. The same is true for every 0 of function of z, as this z equal to z0 is a 0 of this function. Similarly, the same is true for every 0 of the function of z. Hence, all zeros of function of z are isolated. Isolated means except this point, function of z not equal to 0 in the neighborhood. Only at the point z equal to z0, function of z equal to 0, means z equal to z0 is isolated point, means in its neighborhood, function of z not equal to 0, and at this point function of z equal to 0. So this point z equal to z0 is called isolated. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.